Today, we're diving deep, and I mean atomic level deep, into the engineering that literally powers our modern world. Have you ever looked closely at, say, the anti-reflective coating on a camera lens? Or the ultra-hard finish on industrial drill bits? Or even the microchip inside whatever device you're using right now? Well, you're actually looking at the direct results of one of the most insanely precise manufacturing techniques ever devised.
So here's a wild question. How exactly do you paint a surface with a layer exactly 1 atom thick? Seriously, think about it. How do we take a solid block of metal, like titanium or gold, and gracefully lay it down onto a surface, atom by atom, to build these incredibly uniform thin films? Well, we do it through a highly technical, absolutely fascinating manufacturing concept called sputter deposition. And spoiler alert, we don't just melt the material. No, we have to create a perfectly controlled atomic storm.
Okay, let's take a quick look at our agenda for today. First, we'll cover the sputtering phenomenon. Second, physics of the collision. Third, mastering thin film deposition. Fourth, reactive sputtering and HIPIMs. And finally, from smartphones to space.
Right, let's kick things off with Section 1, the sputtering phenomenon, a subatomic breakdown. So what exactly is sputtering? Technically, it's a highly specialized method of physical vapor deposition, or PVD. But the absolute crucial thing to remember here is that sputtering is a purely kinetic phenomenon. We're not using heat to melt a solid into a liquid and then boil it into a vapor. Not at all. Instead, we're using raw physical momentum to basically overpower the solid state of our target material. By bombarding our solid target with highly energetic particles, usually suspended in a localized plasma, we literally knock individual atoms loose from the surface. We physically eject them right into a gas phase, which gives them the freedom to drift through a vacuum and evenly coat our desired surface.
Moving on to Section 2, physics of the collision, playing atomic billiards. To really wrap our heads around how we knock those atoms loose, I want you to think of an incoming energetic ion like a cue ball, smashing into a perfectly racked set of billiard balls. When that energetic ion slams into the tightly packed atoms of our target material's lattice structure, there is a massive, instantaneous exchange of momentum. This sets off what physicists actually call a collision cascade. The energy just rips through the atomic lattice. The incoming ion hits an atom, which hits another, which hits another. And if this cascade of kinetic energy redirects its momentum back up toward the surface with enough force, boom, a surface atom breaks its chemical bonds and is violently ejected right out into the vacuum. But here's the catch. This ejection relies on a very strict mathematical threshold. To break the binding energy holding that surface atom in place, the incoming ion has to strike with an energy specifically between 10 and 100 electron volts. This is basically our physics Goldilocks zone. If the energy is too low, under 10 electron volts, the incoming ion just harmlessly bounces off. Nothing happens. But if the energy is way too high, shooting up into the thousands of electron volts, the ion actually shoots past the surface atoms and implants itself deep inside the material's crystal lattice. So we need exactly 10 to 100 electron volts to get that perfect momentum transfer and knock the atom free. I know. When you put all these concepts together, it honestly sounds like we're describing some intense sci-fi space battle. I mean, we've got ion bombardment, aggressive heat spikes melting microscopic pockets of a crystal lattice, collision cascades, and my personal favorite, something ominously called target poisoning. But I promise you, instead of destroying an alien mothership, these aggressively named events are just everyday, highly controlled physics happening inside a manufacturing vacuum chamber.
Let's jump to Section 3. Mastering thin film deposition, from chaos to control.
You might be wondering, why go through all this trouble with collision cascades in the first place? Well, because compared to traditional thermal evaporation, sputtering is an absolute game changer. It's the ultimate engineering solution. See, if you just try to heat up and evaporate certain metals, they will stubbornly refuse to melt, or the process will be wildly inefficient. But because sputtering relies on physical momentum instead of heat, we can easily vaporize materials that have insanely high melting points. Plus, because those sputtered atoms are flying out with immense kinetic energy, they don't just gently float and condense onto our substrate. No, they smash into the surface. They literally splat and embed themselves slightly into the material, and that creates a thin film with vastly superior adhesion and structural integrity. Let's walk step by step through how this magic actually happens in the real world. First, we put our target material and our substrate into a chamber and draw an extreme vacuum to suck out all atmospheric contaminants. Next, we pump in an inert gas, almost always argon. Argon is the superstar here because it's heavy enough to act as that perfect cue ball for momentum transfer. Then we flip the switch on a massive high-voltage electrical field. This voltage rips electrons away from the argon atoms, creating a glowing plasma of positively charged argon ions. Finally, we apply a strong negative electrical bias to our target material. And since opposites attract, right, those heavy, positively charged argon ions are violently accelerated out of the plasma, crashing directly into the negatively charged target. This kicks off the collision cascade, sputtering the target's atoms off to drift across the vacuum and perfectly coat our substrate. All right, Section 4, Reactive Sputtering and High PIMs, Engineering the Next Level. Now, depositing pure metals is incredibly useful, but to build modern microelectronics, we need complex chemical compounds, and that's where reactive sputtering comes in. By introducing a reactive gas, like oxygen or nitrogen, into the chamber alongside the argon, we unlock a whole new level of chemistry. We aren't just moving pure titanium from point A to point B anymore. As the sputter titanium atoms fly through that highly energized plasma, or even right as they land on the substrate, they chemically react with the nitrogen gas. They actually bond together in real time, forming a dense, completely new crystalline structure. In this specific case, we'd be depositing a highly durable thin film of titanium nitride. But navigating this chemical reaction is incredibly tricky. It's a very delicate balancing act. If you stay in a purely metallic mode, your deposition is super fast, but you don't get that desired chemical compound. The transition mode is the sweet spot. That gives you the ideal perfectly balanced film quality. But, and this is a big but, if you pump in too much reactive gas, you hit the dreaded poisoned mode. In this state, the reactive gas doesn't just bond where you want it to on the substrate. It actually reacts with the source target itself, coating it in an insulating compound layer. And when that happens, your target completely stops conducting electricity effectively, your deposition rate basically plummets to zero, and the entire system suffers from severe instability.
So to overcome this target poisoning and to achieve ultra-dense films, engineers developed something called high PIMs. That stands for High Power Impulse Magnetron Sputtering. Try saying that 3 times fast. Instead of a steady, continuous stream of power, high PIMs delivers absolute extremes. We are talking about power densities that are equivalent to the output of a small power plant, all localized down to just a few square centimeters on the target. It's wild. But these pulses only last for tens of microseconds. Because the power is pulsed so incredibly fast, the target actually has enough time to cool down and avoids melting. Yet, those massive instantaneous spikes of energy create a highly ionized metal plasma, which gives us incredibly dense, void-free thin films with unmatched hardness.
And that brings us to Section 5, From Smartphones to Space, Real-World Applications.
So why does all this invisible subatomic billiards actually matter to you? Well, sputtering is the unsung hero behind almost all of our modern tech. Just think about the sheer variety here. It is gentle and precise enough to lay down the ultra-delicate anti-reflective glass on your camera lens or the highly precise magnetic layers inside a computer's hard drive. But at the same time, it is robust enough to create the rugged, gold-colored titanium nitride hardcoats that they put on heavy-duty industrial drill bits. It truly is the invisible force making our world more efficient.
In fact, I bet you didn't know that this is exactly how premium smartphones get their finish. Apple actually used HIPMs to coat the structural stainless steel band of the gold iPhone 12 Pro. By utilizing this extreme pulse technology, they didn't just get a visually beautiful gold color. They achieved a highly dense, incredibly robust atomic coating that could easily withstand daily wear and tear, all while still functioning perfectly as the phone's intricate antenna system. It's just brilliant engineering. But here is something truly awe-inspiring. Sputtering is not just a human invention. It's actually a fundamental kinetic property of the universe. In a process known as electronic sputtering, highly charged mega-electron-volt sulfur ions from Jupiter's massive magnetosphere naturally smash into the surface of its icy moon Europa. And because the ice is an insulator, the intense energy from these cosmic impacts isn't quickly absorbed. This causes an absolute explosion of up to 10,000 water molecules into space per impact. The highly technical manufacturing process we use in our pristine labs is quite literally mimicking the raw, natural forces of the solar system. How cool is that? As we wrap up this explainer, I want you to take a close look at the screen you are using to watch this right now. Every single pixel illuminating your face is filtered through impossibly thin layers of materials, layers that were painstakingly placed there atom by a synthetic plasma storm. We have mastered the art of atomic billiards to build the devices that literally define our era. So as our control over this kinetic dance becomes even more refined, what impossibly complex technologies will we build next?